X-ray spectrum of alpha from pair. Yeah,
Too long.
Oh yeah. Yeah, but anyway, it's also a very different topic from the previous one. So let's welcome the speaker.
Hi, I'm Tomoki Wada from NTHU. Today I'd like to talk about radiative acceleration and X-ray spectrum viable. First of all, I would like to introduce myself because I am a newcomer of this conference. My name is Tomoki Wada, and here is Chinese character, and my research topic is mainly theoretical study on high energy astrophysics. And I got PhD at Kyoto University, and next moved to University of Tokyo at Japan, and next moved to Tohoku, and now I came to Taiwan. And my research topic so far is gravitational wave and fast radio bursts and magnetars. Today I'd like to talk about FRB and magnetars. Okay. And first of all, I'd like to briefly introduce what is fast radio burst. Fast radio burst is the brightest radio transient in the universe. In the left panel, here is light curve of fast radio burst. You can see a steep spike here, and this is FRB. Okay, thank you very much. This is FRBs. And FRBs is brightest radio transient in the universe. Its duration is, as you can see from here, it's about millisecond, and its luminosity is about this values. And it comes from cosmological distances. If FRBs comes from our galaxy, then the sky map should be aligned our galactic plane. But this right panel shows FRBs, observed FRBs, and it came a bit uniformly from us, from the universe. So it indicates that FRB comes from cosmological distances. And the source and emission mechanism of this FRB is not clear. And among many FRBs, there is very unique FRBs. This one. This FRB was associated with X-ray short burst from galactic magnetar. So about this event, we know what is the source of FRBs. It's galactic magnetar. Magnetar is a neutron star with a strong magnetic field in the universe. And this gray line shows the X-ray light curve, and this orange line shows the FRB light curve. From this observation, we know that FRB luminosity is 10 to minus 1,000 times X-ray luminosity. So, in this event, X-ray is main event, and FRB is additional one. So, from this point of view, we should know what is unique in this X-ray event. And let's move to X-ray spectrum of this FRBX. Here is a plot of cut-off energy and X-ray flux in many X-ray bursts. And this vertical axis shows the cut-off energy of X-ray. And here is very nice picture of cut-off energy. When we plot flux compared with energy, there is strong break, and this is cut-off energy defined in these equations. From observation, we know that X-ray, cut-off energy of many magnetar bursts are about 10 keV. However, about FRBX, its cut-off energy is much higher than other ones. So there is a huge gap between usual magnetar bursts and FRBX. And this is one question about this FRBX event. So there is mainly two questions. One is why is E cut high compared with other bursts? And second question is what is the energy budget for FRBs? in some X-ray events, there should be some energy budget that creates FRBs with this illumination. And before considering these questions, I think I should briefly explain how X-ray is emitted from magnetars. This is very schematic picture. And question there is, how are X-rays emitted from magnetars? First, some energy release around magnetar occurs. It may be a stark wake or reconnection of magnetic field in magnetars. And soon, this released energy is thermalized and fireball is created. Fireball is electron, positron, plasma strongly coupled with photons, like via this process. And at first, its temperature, so the temperature of this fireball is very high and it is optically thick. It means X-ray photons cannot escape from these created fireballs. But as time proceeds, as it expands, it is adiabatically cooled. And as a result of cooling, the number density of electron-positron pair decreases. And at some radius, the optical depth becomes lower than unity and X-ray photon escapes. This is the main story of X-ray emission from magnetars. And by considering detailed modeling of this X-ray, this fireball, we can expect that if fireball is created in if fireball is confined in a closed magnetic field line, then the typical X-ray energy should be about 10 keV. So these usual guides are easily explained by this scenario. A fireball confined in a strong magnetic field. But this FRBX is not created in this scenario. So we should another way to create this high cutoff energy. Then let's go back to original problem. Why is E cut high? And what is the energy budget for FRB? And our answer is outflowing fireball scenario. First of all, first question is, why is E cut high? And our answer is relativistic Doppler shift. In previous explanation, we consider fireballs confined in a closed magnetic field. But if fireball is created near polar region, it expands along magnetic field, and as it expands, this fireball is accelerated by its own radiation pressures up to relativistic speed. And so, although this fireball is adiabatically cooled, but due to Doppler shift, its observed photon energy can be higher than 10 keV. So from this scenario, we can expect higher cutoff energy than usual ones. And second question is, what is the energy budget for FRBs? And our answer is relativistic plasma outflow. As I mentioned the fireball is composed of electron-positron plasma strongly coupled with radiations. And as it expands, the plasma is accelerated. And at final, relativistic plasma outflow can be created. And this plasma outflow can be a possible origin of FRB energies. So if we consider outflowing fireball, it is created near the magnetic polar region. And Doppler shift can explain high cutoff energy, and plasma outflow can be the energy budget for FRBs. And can be the energy budget of FRBs. And next, in this study, we calculate how fast this outflow is and what is the X-ray spectrum from this kind of fireballs. To calculate this plasma outflow and radiations, we we conduct the first self-consistent simulation of radiation hydrodynamics in a strong magnetic field. Okay, let's consider the effect of strong magnetic field. This is not usual MHD, but a bit different from. Sorry, this is not usual radiation MHD, but the scattering section is a bit different. Okay, first we should consider the effect of resonance. In strong magnetic field, electron and positron gyrate around its magnetic field. And if X-ray wave comes from if X-ray is injected, then this electron positron oscillate and emit another photon. This is usual scattering. However, if magnetic field exists, then the motion of electron positron pair is not the same as vacuum, not the same as the motion in vacuum. And I think this is not the exact equation, but it follows this kind of equation of motions. And if omega b gyro frequency is equal to the frequency of X-ray photon, then resonance occurs. And electrons are resonantly moved. And this is, as a result, the scattering cross-section changed. Here is the scattering cross-section compared with photon frequency. Here is the frequency where, here is omega b, and as you can see, at omega is similar to omega b, the scattering cross-section is much higher than Thomson scattering cross-section. So, in strong magnetic field, photons are resonantly scattered by electrons, and we take this effect into account. And here is a simplified electrical equation and method. We assume spherically symmetric and steady flow, and plasma dynamics is determined by radiation force, and radiation transfer is determined by plasma scattering. And from plasma calculation, we calculate number density and temperature. And from this information, we calculate radiation. And from this, using the result of radiation calculation, we evaluate radiation force. And next, use this result, we calculate the plasma, and we iteratively solve radiation and plasmas and find convergent solutions. Okay, speed up. And here is the result of plasma flow velocity compared with radius. And this red line shows the flow velocity of plasma outflow accelerated by resonant scattering. And this black line is the velocity without resonant scattering. So as you can see, the resonant scattering enhances the flow velocity of plasma outflow. And as a result, the kinetic energy of plasma outflow can be higher than the luminosity without resonant scatterings. And here is the obtained X-ray spectrum, and yellow region is the observation, and this solid line is a result of our calculation. And our calculation creates the spectrum consistent with observations. Here is a summary of my talk. Thank you very much.
Okay, thanks. The speaker, questions?
In your simulation, did you take into account of the magnetic connections? Because this fireballs usually, from my knowledge, I thought fireballs usually happen in the magnetic reconnection.
In my calculation, magnetic reconnection is not taken account. In my calculation, the energy density of magnetic field is much stronger than fluid. So fluid cannot move magnetic field. So we assume that magnetic reconnection will not occur in this calculation.
Short question.
Thanks for nice talk. Could you tell me why the luminosity of FRB is 10 to minus 3 compared to the luminosity of X-ray? Could you give me a explanation?
No.
Explanation?
We cannot, in analytic calculation, we know that if Lorentz factor is about this, plasma outflow can be the energy budget for FRBs, but we don't know why this is 10 to minus 3. We only know that kinetic luminosity can be higher than this value.
I see. Thank you.
Okay, I think we need to start to fix